Okay, so in this video, we're going to talk about mathematical proofs. Proofs are the most important, is the most important part of mathematics. I think that's how you spell proof. But spelling isn't important. Okay, so what is a proof? A proof is a set of logical statements. So a statement would include, let's see, what would a statement be? This is actually a drawing of a tree. Now, this could be either true or false. Now, you might say that's not a tree, in which case it would be false, but if it does look like a tree, or at least it looks like I was trying to draw a tree, then the statement will be true. Every statement can be either true or false. A proof is a set of statements. So, set of statements. It's an ordered collection of statements. Where each statement implies the next. So these arrows mean imply. And we go from a theorem. We go from a set of assumptions into what we want to prove. So this would be a theorem or a corollary or some other word. So theorem. Don't worry about the spelling. Okay, you can always Google the spelling if you need. So an example of a very simple proof would be the proof that A plus A is equal to 2A. And this is what we call an identity. And we can prove this pretty directly if we allow for factorization. So we can factor an A. So this is what we will call our theorem. Okay. And this is how we prove it. So we first write down the left-hand side. That's equal to A plus A. Now we factor out the A, and we get 1 plus 1 times A, right? And then now we can do 1 plus 1, which is 2 times A. And this is equal to the right-hand side. And this will be the end of the proof. So this is what we call a direct proof. And there are several other types of proofs. So the types of proofs include direct. There's proof by exhaustion, proof by contradiction, proof I don't think you need to know proof by induction, but there is proof by okay, so another type of proof is called a disproof. I know this doesn't sound like a proof, but it's a disproof by counterexample. So in this case, we'll be proving the theorem is false. Actually, not theorem. The statement is false. So I think disproof by counterexample should go first. So one good disproof by counterexample would be the statement that x squared plus I think it's 41x plus 41 is prime for x greater than or equal to 0. I think that's how you do it. Let me just double check. I think that's right. Yeah. So let's try it for x equals 0. If x equals 0, then x squared becomes 0. 41 times x becomes 0. And then so we just left with, in fact, let's call this y. That means y is equal to 41. And 41 looks prime to me, but you might want to check that. Let's try x equal to 2. Sorry, 1. Let's try x equal to 1. Then we have y is equal to 41 plus 41. Actually, do you remember how to check if 41 is prime? You check all the numbers, all the primes. Check if all the primes less than 41. So what primes less? The square root of 41. All the primes less than the square root of 41. Divide 41. And if none of them do, then 41 is prime. So that's how you check. And if you do check, then you'll find that 41 is in fact prime. So x squared is 1. That's just 41 plus 41, and that is equal to 83. And I'm not sure if 83 is prime. Let's just check. So square root of 83, well, that's just bigger than 9, so we can just say it's about 9. So all the primes less than or equal to 9 would be 2, 3, 7. Obviously 2 doesn't divide 83 because 83 is odd. 3, well, no, because 81 divides 3, right? And so that means if you 83 is 81 plus 2, so 83 does not divide 3. No, 3 does not divide 83. Sorry. And so what's 7? Well, it doesn't look like. Let's just, well, so if we could take away 70 from 83, and that gives us 13, and that doesn't divide 7 because 14 divides 7, right? And then so that means so that means 13 has a remainder of 6 when you divide by 7, so it's not divisible by 7. Okay, so '83 is prime. So we might look at this and just maybe say, oh, it's going to be prime for every value of x. But I encourage you to try and find an example of x that for which this is not prime, and then we'll prove that this statement is false, and that will be a disproof of this statement by counterexample. Can you think of any x's? So one obvious x that you might be able to notice, I mean, it's not that obvious, but what about x equals 41? Well, if x equals 41, y is equal to 41 squared, which is 41 times 41, plus 41 times 41, plus 41. So that means it's equal to 41 multiplied by 41 plus 41 plus 1. That is equal to 41 times 83. And that means y is not prime. Okay, so this is a counterexample to this statement. Y equals x squared plus 41x plus 41 is prime. So this is a disproof. So this statement, I'll call this statement capital P. So therefore, P is not true. Now I don't know if I wrote this right, but this is actually called this quadratic was actually found by Euler, and if you test it for different values of x, for every value less than 40 and every value of x less than 40 and bigger than or equal to 0, this is actually prime. So it's a very long so it gives you quite a lot of primes, but it doesn't always give you primes, and that's what this disproof shows you. Okay, so what about proof by exhaustion? Well, proof by exhaustion is, and we've seen proof by contradiction before, that in some of the previous videos that I've made. And this is a direct proof. Direct proofs are usually, well, if you know how the common algebra techniques, the commonly used algebra techniques, and I will go over them in one of the future videos. Then most of the time, direct proofs are pretty much like this. You take the left hand side, do some algebraic manipulation, get to the right hand side, and that's it. Contradiction usually requires some sort of trick, and I've gone through the proof of infinite primes and the fact the square root of 2 is irrational. Okay, so what about proof by exhaustion? So proof by exhaustion would be a proof where you check all the possible cases to check whether or not something is true. So a proof by exhaustion that we've already seen is checking if a number is prime. So for example, checking if 23 is prime requires you to exhaustively check whether all the prime numbers less than square root of 23 divide 23, and if they don't, okay, if they don't, for every prime less than square root of 23, then this means that 23 is prime. So let's check. So square root of 23 would be something just less than 5, because 5 squared is 25. So we need to check all the primes less than 5. So that's just 2 and 3. And you can check that 2 doesn't divide 23 and 3 doesn't divide 23. And that means 23 is prime. And that's all the different proof techniques. Although questions can be difficult, and in fact it might not even tell you which type of proof you're supposed to use. But yeah, that's about it.